Welcome to the lecture on elasticity this time, and we are going to look at what it is and how you calculate elasticity. So before we go there, why do we need it? Well, we are interested in the relationship between variables, so sometimes we are keen to know how important a variable is and how do we measure that one. If I have a regression model and I find that I can describe y as a plus b, x, and so on, and let's say my b variable is 0.5, okay, what is this telling me about the importance of x to y? Well, it's difficult to look at the size of the coefficient and see if it's better or more important than another coefficient. So this could be 0.2 for x2. So by looking at these slope terms, I cannot say that this is more important than that one, because the slope could change. If I scale the variables, as we have been discussing earlier, in terms of scaling and so on, then the coefficient would change. So that is a good reason why I cannot use the slope as a measure of how important a variable is. So what could I use to see which variables are more important than others? Well, fortunately, we have something called elasticity to use for that. So elasticity can be used to compare how important variables are, and I will explain what that is. But before we do that, let's go and look at its definition. What does it measure? Well, the first thing you will know is that elasticity is a unitless measure. What does that mean? Well, it means it doesn't depend on the unit. So whether you measure your rainfall in inches or millimeters, the impact of rainfall on yield expressed in terms of elasticity is going to stay the same. And this is very good because we already said, well, changing the units shouldn't change the story, and the elasticity is going to do the same. It's not going to change because you change the units. Now, how does it do that? Well, it's sitting here in its definition. What exactly is elasticity? Well, elasticity is a measure of responsiveness. How well does y respond to x? And that responsiveness is measured in terms of proportionate change, not in terms of absolute, in terms of proportionate change. So what that means is we are looking at what happens if the x variable increases by 1 percentage point. Does y increase by more than 1 percentage point? Does it decrease by or increase by less than 1 percentage point? Okay. And if the relationship between x and y is negative, we are interested in knowing what happens to y in terms of decrease when x goes up by 1%. Does it decrease by more than 1% or by a smaller amount? So how well does it respond? So that's why it's called elasticity. Okay, how elastic is y when x changes? And elasticity is measured not in terms of absolute change, it's measured in terms of how much it grows in proportionate terms. So that's what elasticity is. It's a unitless measure, like the raw correlation coefficient. It doesn't depend on the units and is insensitive to scaling. Its definition is here. It's a ratio of the percentage change in y relative to the same in x. And of course, we know what percentage change is. It's simply change in y over y. And if you are thinking of small changes, that's going to become basically small change in y, which is like the differential in maths, dy. But if we do that, we can write this ratio between the two proportionate changes in terms of what you see here. Okay, for small changes, But if you rearrange that, it's going to give you this. Now we have something we recognize, that one. The change in y over the change in x is our slope term, and we know what the slope term is. It's our beta, the coefficient. So if you take the slope term, multiply it by the ratio of x to y, it's going to give you this, and that is what we call elasticity. So that's what it means, and if we need to calculate elasticity for different models, it's good to know some basic facts that tend to be very useful in this case, and this is from calculus. Now, because we'll have our models, sometimes the dependent variable is logged, sometimes the x variable is logged, sometimes both are logged. So we need to know what it means to take the derivative of the logged value. Well, if you take the derivative of a logged value with respect to x itself, you get 1 over x itself. So this is something that probably is not apparent to some people, but that's a useful fact because a lot of modeling has logged values and you cannot avoid having to know about this. Now, most people would know this. This is basic rule in calculus. If you have your x variable exponentiated to a degree n, when you take the derivative with respect to x, your n is going to come down as a multiplier down here. Of course, a is a constant, so constants always hang on when you take the derivative, and then the exponent is going to be n less 1. So that's another fact. What is the derivative of x with respect to y? Well, it's the inverse of the derivative of y with respect to x. It's the same thing, inverted. So this is basically telling you if you had an equation which said y equals a plus bx, that's the slope, change in y with respect to x. Well, if you inverted this so that you had something called c plus dy, okay, I don't mean do that, but mathematics doesn't care. If you invert it, then d is equal to 1 over b. It has to be. And that's a good simple example of why this is true. Now, we said if you take the derivative of a logged value with respect to x, you are going to end up with 1 over x. What happens if you do the derivative of x with respect to its logged value? Well, you will end up with the inverse. So that's what happens because that implies this. So these are simple rules. You can have more, but let's first look at examples. So this is my expression. I want to take the derivative with respect to x. Of course, 12 is a constant, so it will disappear because it doesn't change with x. It's just a constant. But this one, now what I have is a multiplier 0.5, but I have log of x, so it's going to become 0.5 times 1 over x because the derivative of log of x with respect to x is 1 over x. Now I have a cubic function here, and it's a good example of what you have to do, and it's simple. Well, if I take the derivative, in this case, that's going to disappear. That's going to become 1.5. That's going to become 0.2 times 2, which is 0.4. And then I have x to the power of 2 minus 1, which is just x. And this one is going to be 0.1 times 3, which is 0.3, times x to the power of 3 less 1, which is x to the power of 2. So that's what we would find. Now, if we look at just one more fact, you can think of the change in the logged value as it goes, right? And this is just using what we have just discussed to show you that actually this becomes that one, okay? It becomes the change in the proportionate change in y as a result of change in x, and that simply means the percentage change in y due to a unit change in x. So the main thing here is you can think of the change in logged value as a proportionate or percentage change. And this is a useful fact that we'll be exploiting. So let's look at examples of how you calculate elasticity. If you have a linear function, and if elasticity is simply percentage change in y over percentage change in x, we showed that this was change in y over y, change in x over x. Well, and we rearranged this and just said x over y. But in this case, this is simply our a in here. So that's our a, that's a slope term. That's that one. So in this case, what we do is take the slope, multiply it by x over y. That's how it works. So if I have a regression like this, x and y, the slope is constant, so that's a, but the elasticity will vary because these two values will vary depending on where I am on the line. Okay, so that's for the simple case. Now, if we have a log-log form, and we said the change in log value can be taken as a proportionate change, well, then the change in the log value of y with respect to the change in the log value of x is, this is a proportionate change, this is a proportionate change. So the ratio is elasticity itself. So we don't have to worry about that. So the a value here becomes our elasticity. Okay, that's how it works. It's the simplest form of elasticity, which is the slope for the relationship not between y and x, but between the logged value of y and the logged value of x becomes the elasticity. What happens if we have a log linear? Well, in this case, a1 is simply the change in the logged value of y with respect to the change in x. Okay, and we know the change in the logged value is a proportionate change itself, but we have just x here, not the proportionate change. So to turn this into a proportionate change, I can divide this by x, but doing that is the same thing as multiplying this by x. Well, then to keep the balance, I have to multiply this by x. So if I do that, I get elasticity on this, and that elasticity has to be equal to that one. So that's what we have here. So if you have a log linear, you have to take the slope for log of y versus x, and multiply it by x. So that's how easy it is. What happens if we have the reverse, linear log? Well, linear log, now the slope term, a1, in this case, is equal to change in y with respect to change in log of x. Well, we already said this is proportionate change, so we don't have to worry about it. But change in y is not proportionate change, so I need to divide it by y. Okay, whereas this one will take care of itself because that's what it is. So I need to divide this by y because I divide by y here, I need to divide it by y, and that's what we have here. So we have an example here, a linear log. And suppose you are asked to find out what the elasticity is when y is 2. Well, this is linear log, so we know what we have to do. We have to use that formula. And if we use that formula, then our A is 1.2, and we have to multiply it by 1 over y. So we have to do that, and our elasticity is simply 0.6. And I have written here in elastic because a 1% change in x leads to a smaller proportionate change. You can't ignore the sign. It could have been minus 0.6, but numerically it's still smaller. So when you think of elasticity, don't worry about the sign. It's about the magnitude. This is a less than proportionate change. Okay, so that's why we say y is inelastic with respect to x, because it is not giving us a proportionate or a higher change. It's giving us a less than proportionate change. Log linear, okay, so we have this. Now this is a quadratic function of an x variable. Our x variable here is education. Suppose the log of hourly wage is described as what you see here, and you have been asked to find out what the elasticity of wage would be with respect to education, and you are supposed to evaluate at a level where education is the average. This is from the 1991 US wage census or population survey, and the average education at that time was 13.12 years. Well, the first thing we want to do is, first, this is a log linear, so what's going to happen is we are going to use, for a log linear, we need that formula. Okay, so we'll take the slope, multiply it by the x value. Now we don't have a single x value here. Actually, our x value shows up in different places, so we cannot just take that one, because it's not this term, but also this term is a function of our x variable, which is education. So what should we do? Well, first, before we go anywhere, let's find what the derivative of the log of hourly wage is. I am going to call it y to make it simple so that I don't have to write all HR wage. And what's the derivative of that with respect to our x variable, which is education, but let's say education. Well, that's minus 0.042 plus, now this is where we use our calculus. So it's a quadratic term, so 2 will come down, multiply 0.005, so that will become 0.01, and education to the power of 2 will become just education. So my slope term is going to be 0.01 times education. But to get the elasticity, I have to multiply this whole thing by education itself, because this is like my A1, this is my X, and that's what we did here and here. So that's the expression in parentheses, and that's my education variable. So we go back to this one. So that's what we have. Elasticity is going to be minus 0.042 plus 0.01 education times education. So if we do that, we can find out that this is 1.17. So what this is telling us is, if someone increases their level of education by 1%, their hourly wages go up by 1.17 percentage points. So this is elastic, because the response is more than proportionate. So that's how it works. Basically, you can figure out why this formula works based on what we have discussed, but if you don't want to do that, just go and grab the formula and apply it. Okay, so we have already covered what elastic and inelastic are. So y is elastic with respect to x if the elastic value is either greater than 1 or it's less than -1. So it's outside the -1 to 1 range. Or if you prefer, you can always say that the absolute value of the elastic value is greater than 1. So that means it's either bigger than 1 or less than -1, but whichever it is, it means y responds to x more than proportionately. So it's elastic. If it's within the -1 to 1 range, we say it's inelastic. And if it's exactly 1, then we say it's unitary elastic. Well, you might be wondering what exactly could be unitary elastic. Well, here is where you can test what we have discussed. If y is b times x, and y is proportional to x, well, in this case, what's going to happen? Well, the elasticity is going to be 1. Why? Because if x grows by 1%, y has to grow by the same percent. But if you want to apply your formula, you can do it. And what it is, well, elasticity is slope, which is b, times x over y. Okay, then that means b times x, but y itself is b over x. So this will disappear and become 1. Or if you want to try the log version, y equals bx simply means log of y equals log of b. We just take log of the number, the coefficient, log of x. So what that means is we have an implicit 1 here. So this is a log-log, and we know in a log-log, the slope, which is what we called a1 before, but is now 1, is our elasticity. So that's unitary elastic, if you are curious. So that's how it works. And elasticity is a unitless measure, can be calculated easily for different functional forms. And if you are wondering why we care about whether something is elastic or inelastic, well, it's a measure of how important a variable is. So if I have to go back to our initial question, if I have a model and it has more than one variable, and if I cannot use the slopes to say which one is more important, well, then I am going to take elasticity of y with respect to x1 and compare it with elasticity of y with respect to x2. So is the absolute value of this bigger than that, or equal, or less than? And if it's bigger, then x1 is more important. If it's less, x2 is more important. That's how I would use to get around the problem of the slopes not being comparable, or a good measure of how important a variable is. There are questions here. Well, if you take consumption of basic necessities, even if the prices increase, people have no choice. They need to survive. They will eat. It's the same with fuel. Okay? You cannot stop driving or going to work or to university because fuel becomes expensive. Well, you will reduce your driving and your fuel consumption, but you don't have the option of just reducing it by a lot, as you would with discretionary consumption, such as entertainment and the purchase of luxury items. So what you are going to do in here is, well, you will respond more, so it's likely to be elastic, but these ones will be inelastic.